I'd like to introduce our next speaker, Professor Gwen Starkman, who's you've seen in many guises during the course of this meeting. He's a distinguished university professor and professor of physics and astronomy here at CWRU, and he also directs our Institute for the Science of Origins and the Center for Education and Research in Cosmology and Astrophysics. And I want to thank him, as well as my other colleagues, Brian Lynn and Pavel Pavlias-Perez, for their role in organizing this, this extraordinary meeting. So turn it over to Gwen now. Thank you.
So about 2 months ago, Brian and I had pretty much finished inviting everybody, and he said, okay, well, I'll take a first stab at setting up the schedule. And he came back about a week later and said, okay, here it is. And I looked at it and said, you've got to be crazy. You have me speaking after Sam Ting and before Steven Weinberg. He said, no, that's when you're speaking, and that's what you're speaking about. And for those of you who know Brian, you know there's no way to argue with him about things that he doesn't want to be argued about. So it's a real honor to be speaking between two people who already were legends when I was an undergraduate, and certainly are no less legendary now for their amazing contributions to the Standard Model. So I'd like to talk about core theory cosmology and start by reminding us that, of course, the Standard Model has had 50 years of data-driven experimental and theoretical success based on solid early to mid-20th century theory and experiment. And it gets a gold star for that. At the same time, beyond the Standard Model, physics has had 40 years of theoretical and experimental effort based mostly on aesthetic and mathematical concerns, and a desire to incorporate gravity despite a priori dim prospects for experimental tests. And so far, maybe with the exception of what we just heard about, no experimental success. And I'm excluding neutrinos from that, even though there are, on the basis that we would have put right-handed neutrinos and neutrino masses into the Standard Model if only we had known to do so 50 years ago. And we're very upset about that. We would love there to be greater experimental successes to go along with with all that theoretical and experimental effort. Cosmology, at the same time, has had 50 years of incredible observational success for what Frank Wilczek calls the core theory, the combination of the Standard Model and general relativity on the basis of observations that we've already heard about, the cosmic microwave background, catalogs of objects, element abundances. In this context, GR is a successful phenomenological framework into which we have to introduce elements beyond those that a priori our Standard Model expectations would have had us introduce. So we have to incorporate, both for observational reasons and aesthetic reasons, things like dark energy and dark matter and inflation. So, and in addition, and we've heard about them already a little bit from Alex Filipenko, for example, about outstanding observational surprises and tensions that are just starting to appear over the last decade. So what I want to do is I want to recall some of those observational and theoretical successes, note some of those observational tensions, and consider whether the core theory may suffice, after all, or where we might really need non-core theory physics to explain the universe. So it's been almost 100 years since we've been thinking about cosmic expansion. In the early 1920s, Friedman used the new general relativity to predict the expansion of a homogeneous universe. And a few years later, apparently independently, Lemaitre provided not just the theory, but observational evidence based on some of Hubble's use of existing measurements to provide evidence that the recession velocities of objects were proportional to their distances if you looked far enough away, with a proportionality constant that we now call the Hubble constant that was the logarithmic time derivative of the scale factor. Hubble refined his measurements and found that the Hubble constant was 500 kilometers per second per megaparsec. a little bit off from today's value. Here it is. You note why it might have been a little bit off. He was only going out to about 2 megaparsecs, where we know that you really have no right to expect the Hubble law to apply. Today we know that the Hubble constant is about 70 kilometers per second per megaparsec, with, as we saw, few percent tensions. And there's an exclamation point after that, because those are significant few percent tensions that we really have to start worrying about. Okay. But most exciting, and you saw the talk by Alex Filipenko, there's cosmic acceleration that we've known about now for, wow, 20 years, and that won the Nobel Prize in 2011. And here is some of the early data. Well, I guess not so. Here's some of the data announcing that discovery, where we see that the Hubble expansion is not following what it was supposed to be following, which was at the time an open universe with 30% matter, matter equal to 30% of the critical density. Instead, it seems to be requiring a cosmological constant. Now, we, of course, have had an enormous amount of input into cosmology from the observation of the cosmic microwave background, and despite claiming that he was not going to talk about the cosmic microwave background, George Smoot mostly talked about the cosmic microwave background. It was discovered first in the early 1940s, looking at the effect of a photon background on stellar CN lines, mostly forgotten. In 1948, Alpha and Herman predicted that there should be a 5K relic radiation. And sure enough, in 1964 and 1965, Penzias and Wilson, using the Holmdel antenna at Bell Labs, discovered a uniform radiation coming from every direction in space. And I think it's really interesting because they published back-to-back papers with some of the folks down at Princeton, and I love the paper from the Princeton folks starts with this description of the instrument they were building in order to look for it, and says, well, while we have not yet obtained results with our instrument, we recently learned that Penzias and Wilson have observed background radiation. They ended with a residual of 3.5 plus or minus 1 degree K. I thought that was very nice of Penzias and Wilson to allow them to publish back-to-back when they had made the discovery. But of course, since then we have learned an enormous amount both about and from the cosmic microwave background. And I want to point out in particular at the moment the Kobe-Firas measurement made in the early 1990s by the Cosmic Background Explorer satellite, which was able to measure the best, and here it is, it's incredibly beautiful. It follows the black body curve. That measurement hasn't really been exceeded. We know that the temperature of the microwave background is 2.728 plus or minus 0.004 K. We've improved that a little bit with some data from WMAP, but really fundamentally the measurement is from the Kobe Explorer still about 25 years later. So, are there tensions with this core theory about the homogeneous properties of the universe, about the cosmic expansion? So you'd think so from that word dark energy. Right? Dark energy implies that we need this new form of energy that, that isn't coming from the standard model, from general relativity. In fact, there are over 5,000 articles on dark energy. Well, the core theory has dark energy. As we learned earlier, it's the cosmological constant. It's been around for almost as long as general relativity. And so the core theory with a cosmological constant of about 0.7 is perfectly consistent with all of the data. There's no compelling evidence for anything non-core about dark energy. We're just terribly uncomfortable that the energy density in this vacuum energy is not zero, even though we were never really able to explain why it had to be zero. And it's also not any of the estimates we would have made from general relativity, our ideas about quantum gravity, our ideas about the standard model. It's just this number that's horribly small, but just not zero. We're uncomfortable, but that doesn't mean it's inconsistent. We should absolutely go and test the null hypothesis that rho lambda is a constant, or W equals minus 1 in the language that Alexei gave us. And we may need some of those alternatives to cosmological and constant to inform where to look. But so far, there's no compelling evidence that they are needed or better explanations of anything that we see. So, no, dark energy is not really in tension with the core theory. Okay, surely dark matter is in tension with the core theory. Okay. Well, what is dark matter? It's non-relativistic matter. We know, we learned earlier that it comprises about 30% of the critical energy density in the universe, or about 30% of the energy density in the universe. But the Standard Model does have non-relativistic matter, as you might have noticed sitting in this room. But how much of that matter is Standard Model? Well, to do that, I think we have to look beyond just the inhomogeneities as tracers, and we have to actually start looking at them. So we can look really far away. This is the extreme deep field. You know, we're looking here at many of these galaxies are, well, I thought they were 13.8 billion years nearly, but apparently they might only be 12.8 billion years old. Somewhere between those. They're really old. We know that many of those galaxies, the ones we've measured, they need extra gravity. The gravity of the luminous matter in them is not sufficient to hold them together. We also know that clusters need extra gravity, and that extra gravity doesn't just act on the non-relativistic matter like the gas and the dust and the stars, it acts on the light. We see that by looking very clearly here in the bullet cluster where we are able to make weak lensing measurements. We're able to map out the matter based on how the light has been bent by the cluster, and we see that the light has been bent by the cluster exactly in a way that we would have expected from dark matter. We look at the cosmic microwave background, and we've noticed that after 30 years of looking at it, we can detect the inhomogeneities in that, the anisotropies in that cosmic microwave background. Here is the most recent map, the one made by the Planck team, the most recent map of the full sky. And we look at that map and we look at its statistical properties, in particular its angular power spectrum. Let me focus on the angular power spectrum of the temperature fluctuations. And we see these absolutely beautiful bumps and wiggles in this curve, in this angular power spectrum. And it's amazing that they are explained by 6 parameters. And one of the things, though, that tells us is that there is a difference between the density of non-relativistic matter and the density of baryons. The baryons comprise about 5% of the total energy density, and the total non-relativistic matter is about 30%, leaving 25% unaccounted for, apparently, certainly as not baryons. So dark matter is apparently not a Standard Model particle, but that is still not evidence of physics beyond the Standard Model. After all, you're not a Standard Model particle, and you're non-relativistic matter. So what do we know about dark matter? We know from the CMB that dark matter thermally decoupled from Standard Model particles by redshift of about 3,000. We know from Big Bang nucleosynthesis that it had to be sequestered from the ordinary baryon, separated by temperatures of around an MeV. And that eliminates obvious non-relativistic matter that would be dark, like white dwarfs or neutron stars or black holes that were formed at the endpoint of a stellar life. It also eliminates things like failed stars and planets mating galaxies. And so the result has been a 40-year heroic ongoing search for beyond the Standard Model dark matter, like WIMPs or axions. But there are core theory dark matter candidates that have been around for just as long as there have been beyond the Standard Model dark matter candidates. Way back in 1975, Chaplin suggested primordial black holes created early in the history of the universe as dark matter. And while it's true that we know that you can't have primordial black holes of a single mass as the dark matter, what this shows is the fraction of the dark matter that can be a particular mass black hole. And you'll notice that there's no empty spot along here, except way up to the right, where we have 10 to the 13th solar mass black holes. Nevertheless, we wouldn't, if we made primordial black holes, we probably wouldn't expect them all to be the same mass. So a spectrum of black holes of different masses is still perfectly acceptable as a dark matter candidate. it's also possible that strange quark or strange baryonic matter is stable. We don't know. We're not yet able to calculate that within the standard model. Way back in 1984, Ed Witten suggested that strange quark matter could be the dark matter. And my colleague Brian Lynn in 1990 with collaborators looked at strange baryonic matter in great detail. And that may be stable, it may not be, we don't know, but if it were, it could be really good dark matter. So here is a plot showing, well, all the colored areas have been ruled out, by the way, only ruled out as if you have all of the dark matter sitting at that mass. So microlensing tells us that they can't be much more, Earth mass or bigger. There's some femtolensing limits that tell us it can't be between about 10 to the 17th or 10 to the 20. People dug up years ago about a square meter of mica and looked for tracks in the mica. And the mica tells us that it can't be below about 55 grams. It can't be too heavy, too low density, that's up here. So this is the mass of the dark matter compared to its size. And if it's too low density, it would disturb the cosmic microwave background. And up here are the revised limits from lunar seismology. But this green line, which are objects of nuclear density, you'll notice that there's a huge range that is completely unconstrained. And in fact, way down, black holes here, all the way down here, there's an enormous range of mass versus size in which the dark matter can very happily live completely within the standard model plus GR. So, dark energy, no, not really in tension with the core theory. Dark matter, not necessarily in tension with the core theory. Surely inflation is clearly in tension with the core theory. You remember inflation? It's an attempt to solve important cosmic puzzles about the homogeneous universe. Like, why is the homogeneous universe so homogeneous and isotropic and flat and old? Why its entropy what it is? And the scenario to solve that is that there was cosmic acceleration not just now, but early in the history of the universe that was able to take place a small region and inflate it to enormous size, and that would explain all of these properties these puzzles that we have been so interested in. And as we heard before, this can happen as long as there is a source of energy density whose pressure is less than minus 1/3 rho, such as vacuum energy with P equals minus rho. There are many, many toy models for the inflaton. And by toy models, I mean models that theoretical cosmologists have dreamed up that aren't the standard model, often aren't connected to good beyond the standard model physics, but have just been put down as things to play with to see what their effects would be and see how what kind of spectrum of fluctuations they would produce, how they could be connected to the reheating of the universe at the end of inflation, etc. And there's a debate whether inflation has solved most of those puzzles or merely pushed them into the pre-inflationary initial conditions. But I think if you look at some of the predictions, they're pretty compelling. After all, they tell us that we should see a nearly scale-free spectrum of adiabatic energy density fluctuations extending to superhorizon scales. Well, you can quibble about the scale-free because we've thought that the spectrum would be scale-free long before inflation. It's really a post-diction of what was called the Harrison-Zeldovich spectrum. But the superhorizon, the adiabatic, and the nearly are really successful predictions. So whereas 10, 15 years ago, we might have said, well, inflation is a theory that post-dicts many things. It hasn't predicted anything. I think that's unfair to say at this point. It's made many successful predictions. It doesn't mean it's right, of course, but it has certainly made many successful predictions, and many inflationary toy models have been constrained or ruled out by CMB measurements. So here is a now classic figure in which we have to live somewhere in here, and various inflationary models, many of them do, and many of them don't. Okay? But all of the ones up here are non-standard model. So is there standard model inflation? Well, the only real candidate field in the standard model for the inflaton is the Higgs. And that appears to not be a very good inflaton if we just have it minimally coupled to gravity. So it seems to require a large non-minimal coupling of the Higgs to gravity that is so far consistent with CMB constraints, and it predicts no visible gravitational waves for inflation. So if we don't see anything when we go look for gravitational waves, that might be suggestive. But if we see gravitational waves from inflation, that would appear to rule out the Higgs as the inflaton. Okay. So is inflation in tension with core theory? Not yet. Maybe one day. But at the moment, no. Inflation could be consistent with our core theory. So is there cosmological evidence for physics beyond the core? Well, I was happy that Rocky suggested that, in his talk about the origin of the baryonic symmetry, that there was a possibility. I think one of the most exciting things about the baryonic symmetry is that it has so much to do with the unprobed standard model physics that converts baryons and leptons that we still haven't measured. It's kind of remarkable that 50 years into the standard model, there's this whole sector of standard model interactions that not only haven't we measured, we don't yet have a good idea of how to measure. And so I think that's one of the great challenges for the people at the back of the room, to figure out how do we actually probe that sector of the standard model that has such an important role to play in the history of our universe, probably. Okay. Experimentally, there are experimentally unexplored standard model neutrino physics that could account for the leptogenesis, and then that leptogenesis result in baryogenesis through the non-perturbative sector of the standard model. So is this non-standard model physics? Yeah, maybe. I think that we can have a semantic discussion, which isn't terribly interesting. I think we were all hoping for something much more exciting in our beyond the standard model physics when we thought about baryogenesis as an indicator of beyond the standard model physics. So we could get lucky and have real beyond the standard model physics, or it could just be more of the beyond the standard model physics that we forgot to write down in the 1960s, or we could have one of those wonderful models of just beyond the standard model physics like Professor Filiviev's talked about yesterday, in which we go out over the next few years and manage to discover beyond the standard model physics just beyond the electroweak scale. So is baryogenesis evidence of beyond the core theory physics? Well, I changed my slides at the last minute after Rocky talk and gave him a question mark here. Okay? Maybe it is. I don't think it's so clear, though. Okay. So going back to that standard model dark matter as evidence of beyond the standard model physics, though, you probably should ask, how do you make primordial black holes or macroscopic dark matter? Because while they are standard model or core theory physics, the hopes for making them that Witten wrote down in 1984 were for a first-order QCD phase transition, which I'm sure Professor Chris sitting in the front row would tell me is a lot less likely at this point than it was in 1984. Okay. And so but it's a question of the spectrum and nature of fluctuations in the early universe. And so while this may or may not require beyond the standard model physics, it may require a standard model of physics that's way beyond our ability to test. So beyond the standard model physics that's at scales that we have no hope to explore in upcoming laboratories. So cosmological evidence for beyond the core theory. Dark energy, definitely not. Inflation, no, not really. Baryogenesis, I forgot the question mark there. And dark matter, maybe we should promote that to a question mark. But it's not, so far it doesn't seem that optimistic for cosmological physics to predict that particle physics is going to become exciting and all about beyond the standard model physics because of the requirements of cosmology anytime soon. But the good news is that there are troubles in the cosmological core theory paradise. And we heard about one of them just a little while ago, right, from Alexei Filipenko, that our measurements of the Hubble constant from the CMB and our measurements of the Hubble constant from lower redshift don't seem to be agreeing, and the disagreement seems to be becoming more convincing. I want to remind you of two others. The first one is something called the radial acceleration relation, which is the observation that when you look at a whole range of galaxies and look at their baryonic content and predict the acceleration that those baryons would produce, and then compare it to the actual the actual acceleration that you're seeing, for some strange reason, the baryonic acceleration predicts the total acceleration. They're of course not equal, because if they were equal, we wouldn't need dark matter in galaxies. But one predicts the other, and that's completely unexpected. I don't think any of us expected that to be the case. And it's not just the asymptotic v squared over r. It's the detailed dependence of the velocity as a function of radius within galaxies that seems to be predictable by observing just the baryons, something we certainly wouldn't have thought would be the case. Could this arise naturally in lambda CDM? Well, if you stay for a couple of days and go to a talk by Dichang Dai at Pascos, you'll see him produce this graph from his recent paper, which suggests that if you look at the Eagle simulation, you find exactly the right relation just from a baryonic simulation. The second one I want to mention is the large angle anomalies in the CMB temperature, in particular this one, which is that if you look at angular separations more than 60 degrees on the sky, the temperature of the CMB is completely uncorrelated. And it shouldn't be. That's not what our model predicts. Our model predicts that there are anti-correlations and then correlations, and instead we see absolutely no correlations from about 60 degrees up. And it's not the only thing that's strange about large angles. The northern sky has low variance. There's an alignment of the quadrupole and octopole. Indeed, if you looked at the graph, the figure that George Smoot showed earlier of the fitting of the angular power spectrum, you'll notice that the Planck power spectrum below L of 50 was excluded because it doesn't actually fit all that well. So if we look at the past, trust the standard model and verify would have been a really compelling 50-year narrative if particle physics had adopted it. Boring, perhaps, but really compelling and really successful. Unfortunately for particle physics, unless we rule out primordial black holes and macroscopic dark matter and Higgs inflation, cosmology doesn't guarantee testable particle physics beyond the standard model. But fortunately for cosmology and for physics, there are abundant opportunities to test the core theory null hypothesis on the sky, and compelling data mysteries whose solutions may lie outside the core theory and whose explanations may have other observational consequences. Thank you.
Questions?
So you mentioned the problems on very large scales, which I appreciate, and I was wondering if these very large-scale galactic surveys that have three-dimensional information could help with those issues.
Yeah. So one of the exciting things is, we notice that in the temperature sky at angles bigger than about 60 degrees, things go wrong with this two-point correlation function, and all the other things are at these large scales. And we're starting to get surveys where you could imagine, that we are exploring those size scales. Now, the trouble with surveys of objects is that the signal on the correlation function at this point has only been measured out to a few degrees. And getting it out to the kind of 60 to 80 to 90 degrees it's the observers aren't confident yet that they will be able to measure the correlation function. In other words, do you really understand that your survey is the same in this direction and this direction? You probably understand it's the same in this direction and this direction, but those large correlations are tough. However, there are lots of other probes. For example, we can look at temperature polarization cross correlations, polarization cross correlations. We can correlate the CMB with future 21 centimeter surveys. We can correlate, so there are many probes. So the good news is the fact that we saw the temperature correlations go to 0 has predictions within lambda CDM, and most of those predictions are that there's no change from what you expected having seen that. But if you have an explanation that says that's actually physics, that absence of correlation, it's hard to imagine that that absence of correlation won't show up in all sorts of other probes.
Okay. Glenn, I just wanted to make a small comment because you mentioned neutrino masses. As I mentioned yesterday, as the standard model was built, you know, they didn't have neutrino masses. And I know that everybody like right-handed neutrino they put in the standard model and they consider that it's part of the standard model. But still, this is not really the standard model. I just want to give more credit to people that spend time building theory for neutrino masses. We don't really know if right-handed neutrinos are there. Maybe there are new scalar fields mediating type 2 seesaw mechanisms or other things. And I want to emphasize that maybe the modification is so tiny because maybe the neutrinos are Dirac and it's so simple that it's not really a big deal. But just to give credit to people, this is one comment. The second comment is about baryogenesis. I personally don't know any mechanism where I could have baryogenesis with the amount of CP violation that I have in the standard model. And this is one of the conditions that I know that the phase transition it can be complicated, but you need CP violation. I don't know any mechanism in the context of the standard model where you, with that amount of CP violation we have in the quartz sector, it's possible if you include, if for you have right-handed neutrino, that there is CP violation hidden in the electronic sector, but I personally don't know any mechanism that you can do baryogenesis with the amount of CP violation that we have.
Yeah, I think if you remember my comment was that you can imagine standard model neutrino, you can imagine leptogenesis from the right-handed neutrino sector, then becoming baryogenesis through the non-perturbative fluctuations. Yeah. So let's. We've had this discussion before, Pavel, and I think what I would say is it's either part of the standard model that we might have written down if we had known, but at least it's an evolutionary change, not a revolutionary change. It's not the huge conceptual change that I think many of us thought we were going to be finding with low energy supersymmetry or extra dimensions or Technicolor. It's an important aspect of an extended standard model. But important. I don't mean to deny the importance of neutrino physics.
Just to go with Pavel, I completely agree with him, and I disagree with the way you presented this. For instance, if neutrinos are Majorana, I agree with you. If the creators of the standard model would have put a neutrino right-handed, maybe they would have thought of writing a Majorana mass term. Is natural. But as Weinberg himself did, the standard model was one thing, and then he added a dimension 5 operator that violates lepton number. What I mean by that is that it's not just a trivial extension to detect the Majorana character. You know, you would have put in evidence that Weyl fermions are essential building blocks, and you have discovered violation of B minus L. So that is, I think that that is a major discovery if we discover, for instance, but excuse me, the leptogenesis that they have been talking about includes baryon number violation. It's based on a not just in a right-handed neutrino, it's a Majorana character for the neutrinos, right?
Thanks.
So shall we thank Glenn again?